In this video, we're going to look at the ways that we can use data about how concentration changes over time, together with the integrated rate laws to actually determine reaction order if we don't know that yet. So essentially, there are two different methods that we can use in order to be able to do this. The first is to take your data, if you have several data points of concentrations at different points in time, and you can plot them three different ways and see which one produces a linear graph. So for a zero order reaction or zero order reactant, the graph of concentration versus time is going to be linear. So if you plot just straight up concentration on the y-axis versus time on the x-axis, you will get a linear result, a linear plot of your data points. For a first order process, it is the natural log of concentration versus time that ends up being linear. And for a second order process, it is the inverse of concentration versus time that ends up being linear. One other little thing to note is that for zero order and first order, the linear plot has a negative slope, but for second order, it does have a positive slope. So essentially, one way that you can determine your reactant order is to take your concentration versus time data and plot that as is. Plot the natural log of all of your concentrations versus time, and plot the inverse of your concentrations versus time. So if you plot your data these three different ways and check on which of them comes out to be a straight line or the best fit to a straight line, that will tell you what order that reactant is. The other thing that you can do is to see how the length of a half-life changes throughout your reaction. So for a zero order reaction, the first half-life is the longest, and they get shorter and shorter after that. So getting from 100% of your starting material to 50% takes longer than getting from 50% to 25%, and so on and so forth. They get shorter and shorter as you go on. For a first order process, we mentioned in the previous video that all of your half-lives are the same length. So if it takes you 30 seconds to use up the first 50% of your material, the next 25% is going to take you that same 30 seconds. It's going to take you the same amount of time. And for a second order reaction, the first half-life is the shortest. So getting from getting from 100 to 50% is going to be faster than getting from 50 to 25, which will be faster than 25 to 12.5, so on and so forth. So what this looks like in data is looking for half-lives, is looking for when is my concentration being cut in half. So in this example, we're starting at a concentration of 1. Starting at a concentration of 1, the first half-life represents going from a concentration of 1 to a concentration of 0.5. So this would be my first half-life here, is from 0 to 20 seconds. So that is 20 seconds long. My next half-life would be going from 0.5 to 0.25 would be my second half-life for this reaction, is going from 20 to 30, is only 10 seconds long. So in this case, my first half-life is longer than my second one. You can assume that that trend would continue if we had more data. Our first half-life being the longest is consistent with this being a zero-order process. You could also do the plotting method for this, that you should find a linear graph for concentration versus time and some kind of curved non-linear plot for the natural log and inverse of concentration versus time. Let's look at one more. So why don't you pause here and try to determine the order with respect to B for this reaction. So I'm going to look at the half-life method again. The plotting method should get you to the same place, but is not as time efficient on the exam. So looking for half-lives in your data, I think, is frequently the better way to go, since you don't want to spend a ton of time graphing stuff in your calculator. So if we're starting in a concentration of 1.2, that means my first half-life is going from 1.2 to 0.6, is cutting my concentration in half. So that is my first half-life, is from 0 to 120. So that is 120 seconds. My second half-life is going from 0.6 to 0.3, is from 120 to 240, is also 120 seconds. Since these two things are the same, half-life has constant length, is consistent with this being a first order process. So if you did do the plotting method, you should find that concentration versus time is nonlinear, has a curve to it, but the natural log is a straight line. So either method works. Sometimes they'll give you graphs on the AP exam as a signal for your reaction order. If they just give you data like this, being able to recognize the half-lives is usually faster.